Okay, welcome back, Chem 212 students, for our third and final lecture about alcohols this week. So previously, we talked about the reduction of carbonyls to make alcohols, and now we're going to go the other direction and talk about the oxidation of alcohols to carbonyls. Now, like I told you before, you could go and calculate oxidation numbers for carbon and see that oxidation is happening, or you can just recognize that we can say two things. We're removing hydrogens, right? We're removing these two hydrogens in the oxidation. So removing hydrogens is oxidation. Or we're going from one bond to oxygen to two bonds. More bonds to oxygen. That's oxidation as well. So that's the easy way to see whether oxidation or reduction is happening, right? If it's reduction, you would add hydrogen atoms, or you would have less oxygen or less bonds to oxygen. And so we're doing oxidation here. So let's talk about oxidation. So oxidation of primary alcohols are going to produce an aldehyde, and this is why. If you have a primary alcohol, the alpha carbon on the alcohol is attached to one carbon. And when you oxidize, you're going to remove one hydrogen here and the hydrogen from the oxygen. You end up with a double bond to the oxygen. So there's one hydrogen remaining, and that results in an aldehyde. If you further oxidize, you will end up with a carboxylic acid. And the way to notice that this is an oxidation, again, is to see that in the oxidation, we've added an oxygen atom. There was just carbon bonded to hydrogen here, but afterwards there's carbon bonded to oxygen bonded to hydrogen. So we have an extra oxygen. So adding oxygen here is oxidation. Now, if you have a secondary alcohol, if you oxidize it, you remove this hydrogen and this one right here. So we're taking off this one, we're taking off this one, and then we had a double bond here. And so you get a ketone. That ketone cannot be further oxidized to a carboxylic acid. And so that's as oxidized as it gets. Now, what about tertiary alcohols? Let's think about that. Tertiary alcohol will not be oxidized like this. Think about why. There would be no hydrogen here, right? So you couldn't do it in the same way. So tertiary alcohols do not undergo oxidation because they don't have any protons at the alpha position. So remember, in both of these cases, we were removing two hydrogens to oxidize here, right, in the first step. You can't do that to tertiary alcohol. There's no hydrogen there. So you can't oxidize the tertiary alcohol. There's all kinds of oxidizing agents that you could use. The most common oxidizing agent is chromic acid that comes from sodium dichromate. So you use chromium trioxide, or you can use sodium dichromate in an acidic environment that will produce chromic acid, which is shown here. Very, very common oxidizing agent, very strong oxidizing agent. So that's not always a good thing, but it will definitely oxidize things. In terms of how this happens, so oxidizing alcohol with chromic acid is going to involve the formation of chromate ester. So the chromate ester will be produced. The mechanism is not given. I don't think that it's completely known. But what's effectively happening here, it's what's known as a dehydration. What's effectively happening is we're removing water. So this is leaving as water. And then H2O. And then this oxygen atom is attached directly to this chromium atom. And that's, so we can see here, this oxygen now is directly attached to the chromium, right? And then when the oxidation happens, the way it works is similar to it's an E2-ish mechanism, because it's going to happen all simultaneously. You're going to have a proton transfer here. So this water grabs this proton, okay? And then these electrons that were in the bond now go into the pi bond to the oxygen. So this is going to start making a double bond here. And then the chromium atom leaves here, and you end up with this bichromate ion. or hydrogen chromate ion, or chromite rather, hydrogen chromite ion, and you get the carbonyl now. And so that's the mechanism here. It's a partial mechanism. You know how I feel about partial mechanisms. You don't got to know partial mechanisms, okay? This is a partial mechanism. The mechanism for this part's not known. Don't got to memorize this, but this is an explanation for how it's occurring. That's where this double bond comes from, is when this elimination happens. Remove this hydrogen, and then these electrons can go into making the pi bond when the chromium leaves. So when you oxidize a primary alcohol, so this is a problem with chromic acid. If you wanted the aldehyde, you're probably not going to get it because it's going to oxidize the primary alcohol to the aldehyde, but then that oxidation will not stop, and it will go on and it will make the carboxylic acid. So if you want the aldehyde, what you do instead is you use a reagent called pyridinium chlorochromate. It is this guy right here. It's a polyatomic cation, a polyatomic anion. If you use the PCC, that's what it's abbreviated as, with dichloromethane, you will get the aldehyde, and so the oxidation will stop there. So synthetically, you want to keep both of these in mind. If you want to go from the alcohol straight to the carboxylic acid, chromic acid is fine, or sodium dichromate. If you want to stop at the aldehyde, you're going to want the PCC and the dichloromethane. If you're oxidizing a secondary alcohol, it doesn't matter which one you use, because remember, the ketone cannot be any further oxidized. So you can use the sodium dichromate in sulfuric acid environment, or you can use the PC with the dichloromethane solvent. Either one will work here. The problem with chromium is that it's really bad for the environment. These strong oxidizing agents, they're terrible. You don't want them, going around. The oxidizing agents are what can cause cancer if you were exposed to a lot of oxidizing agents. Now, in terms of this mechanism, I'm going to show you this mechanism, but you do not need to know this mechanism, okay? You do not need to know this mechanism. This is just kind of odd mechanism that I don't feel like it's necessary to know. But if you hear the Swern oxidation here, and for oxidizing oxidizing alcohol to a carbonyl, first it involves dimethyl sulfoxide and this oxalochloride, which is this. Again, you do not need to know this mechanism, but it involves a nucleophilic attack to this carbonyl, and then a loss of the chlorine leaving group here, and then an attack with the chlorine on the sulfur, because the sulfur's got a positive formal charge here, so the negative formal charge is attached to it. And then the movement here of these electrons here to here, this makes carbon dioxide, and then we get another unit of carbon dioxide when this chlorine leaves, and we get the chlorodimethyl sulfonium ion, and this is what's going to be our oxidizing agent right here. So you have this combination of reagents, DMSO and oxalochloride. And so that's our effective reagent, so the chlorodimethyl sulfonium. And at that point, we've got this sulfur with this positive formal charge because it has these 3 bonds here, and 3 bonds and 1 lone pair not shown. The lone pair here on the oxygen attacks. It's a nucleophilic attack. And then we use the triethylamine as the base to deprotonate that oxygen, because now this oxygen is going to have 3 bonds, 1 to sulfur, 1 to carbon, and 1 to hydrogen still. And so it has a positive formal charge. It gets deprotonated by the triethylamine. Then the carbon here on the neighboring to the sulfur here also gets deprotonated. Finally, that makes a carbanion, which actually deprotonates this carbon and finally results in the formation of the ketone. So this is an alternative, milder oxidizing agent. So the DMSO and the oxalochloride, which makes this chlorodimethyl sulfonium ion, going back a step here. You do not need to know this mechanism. Please don't worry. Don't worry about this mechanism. Okay, if you have a primary alcohol, it will make an aldehyde. If it's a secondary alcohol, it'll make a ketone. Same as before. So knowing the mechanism is not important. You should be familiar with the reagent. Like PCC, if you use DMSO and COCl2 and with a triethylamine treatment afterwards to deprotonate, you'll oxidize a secondary alcohol to an amine or a primary alcohol to an aldehyde. It's a mild oxidizing agent, so it's not like the chromic acid. It will not oxidize it all the way to the carboxylic acid. So this is basically an alternative to the PCC. Just I'd say just stick with the PCC, but this is also in your book, so I thought I'd mention it. An alternative here, another one again, because chromium reagents are terrible. There's other methods of oxidation. Here's another oxidizing agent. Again, another mild oxidizing agent. It's called the Des-Martin pyridine oxidation. Got all this here. That's what the DMP stands for here. And these are acetyl groups here. So all these OACs represent this. So just another way of oxidizing to an aldehyde or a ketone, another mild oxidizing agent. Again, you do not need to know this mechanism. It's in your book. This mechanism is a whole mess. I'm not going to talk about it. The slide's here to tell you. This mechanism is in your book. Do not memorize it, okay? So let's take a look here, though. Let's do an example problem. So I encourage you to pause this and give this a shot, and then and pause it now. Okay, you're unpaused, and let's see what you get. So we're with the alcohols here. Remember, a secondary alcohol is going to be oxidized to a ketone, and so we're going to get here for this first one, we'll get a ketone. And then for this guy right here, we're going to get we got this. It's dashed, a dash, and then we're going to get a ketone or an aldehyde right here. But notice that this is primary, right? There's a hydrogen here. So we're actually not going to get an aldehyde because this is a strong reducing agent. So we're actually going to get a carboxylic acid here. In addition, we've got an aldehyde over here, but aldehydes are also oxidized by this strong oxidizing agent. So we're going to get a carboxylic acid here. So the secondary alcohol is oxidized to a ketone. The primary alcohol here is oxidized to a carboxylic acid. It gets oxidized to an aldehyde first and then further oxidized to a carboxylic acid. And this aldehyde here gets oxidized to a carboxylic acid. So we put an oxygen atom right there between the oxygen and the hydrogen. So there is the answer. Okay, in terms of biological reactions, so some of the payoff for those of you guys that are interested in biology and biochemistry is that when we talk about oxidation and reduction in this style, in the organic style, where we're adding oxygen atoms, oxidation, right? We're removing hydrogen atoms, that's oxidation. These are the kinds of oxidations and reductions you're going to see in complex biomolecules. An example is in the citric acid cycle. Part of the citric acid cycle and many other biological reactions is the presence of this reducing agent called NADH. And NADH, the hydrogen here is the one that can be removed. There's another one also that can be removed. Here is the NADH here, right here. So it's a huge, giant molecule here. It involves various parts. This is called a base. It's called a base because it has all these nitrogen atoms which can accept protons. This is called a sugar or carbohydrate. We'll learn about those in Chem 213. You got diphosphate linkage here. Phosphate groups, this part is basically similar to a nucleotide right here, like DNA. And this is similar to part of a nucleotide too. Uh, so they're nucleotide-like, but this is a reactive intermediate that's a reducing agent involved in biological reactions such as the citric acid cycle, or the Krebs cycle, as it's also known. So these reactions that we're learning are exactly the same reactions that happen in the body. They happen in the same way. They're just directed. They're catalyzed by proteins called enzymes. So they can happen millions of times faster than they might otherwise happen. But for NADH, NADH gives its proton, so that's why I call it a reducing agent. It delivers hydride, and so that involves here this kind of resonance going on, and then finally the delivery of the hydride ion right to the carbonyl, which can also then pick up a proton up from some acid here. There's enzymes directing this, catalyzing this, but at this point we get NAD plus, so it's lost the hydrogen atom. Thus it was itself oxidized, and it causes the carbonyl to be reduced. So this is super common. For some reason this box here went behind in front here. So this is one way that nature in biology converts carbonyls into alcohols. And NAD itself, just like NADH was a reducing agent, NAD plus, after it's lost the proton, is an oxidizing agent. So it can grab the proton back from somewhere. So if you want to turn alcohol into a carbonyl, it will grab that proton there, and then we have those resonance arrows bringing the lone pair back to this nitrogen. And this is a part of the citric acid cycle. The NAD plus, it gets input into the citric acid cycle. It goes through it, comes out as NADH, and then the NADH goes and turns ADP into ATP, and the ATP is the energy. So you're going to learn about the details of this when you take biochemistry later. We'll talk about it a little bit more in Chem 213, and you'll learn even more if you take biochemistry after. Remember, tertiary alcohols, they don't undergo oxidation. Now you might think phenol is like a tertiary alcohol because, hey, there's no hydrogens here, right? But there's no alpha proton, just like a tertiary alcohol. But as we talked about before, phenols are different than alcohols. They're not the same. In fact, phenols can be oxidized even more readily than primary or secondary alcohols. So if you have a phenol, you will oxidize the alcohol to OH. In fact, you'll oxidize twice. You'll end up with a benzoquinone, and so with this strong oxidizing agent, you'll actually oxidize twice and end up with this benzoquinone. And then you can reduce that to hydroquinone, which is the same. You're just reducing it so that the carbonyls here, the ketones, are alcohols, and then it can be oxidized back to benzoquinones. And these interconvert very readily, and this is important in respiration. This ubiquinones here, these are used to catalyze the conversion of oxygen into water, and so that's essentially an important part of our metabolism as well. So these are all metabolic intermediates, and they do the same types of oxidation and reduction reactions that we've been talking about. And again, when you analyze them, you're probably going to want to analyze the easy way that I showed you with, reduction is adding hydrogen atoms, oxidation is removing them, or oxidation is adding oxygen atoms, reduction is removing oxygen atoms or bonds to oxygen atoms, right? And that's an easier way to analyze this, because look what we got. We got carbon, hydrogen, oxygen. When you analyze it that way, it's just easier. So this catalysis here, again, for these detailed steps, do not memorize these. These are just kind of flavor for you to understand why the heck am I learning this if all I care about is biology, right? And we're going to go into a lot more detail when we talk about biochemistry in Chem 213. But you've got a ubiquinone here and a proton. You got NADH that provides the other proton becoming NAD, or the hydride rather, not the proton. It provides a hydride, and you get a double reduction of the ubiquinone. And then this can go on and react with oxygen and become oxidized and produce water. And so the net reaction here is NADH plus oxygen, and one proton produces NAD plus and water. And so these are important biological reactions that involve oxidation and reduction, as we've been learning. So it happens in the test tube, and it happens in your own cells as well. Now, finally, in this chapter, we've added some new reactions. We've got great new reactions here for adding carbon atoms and changing functional groups. These ones here, in terms of converting between alkynes, alkenes, and alkanes, these are all the same. Nothing's changed here. What's really changed is our methods of changing alcohols into carbonyls. This is really new, and interconverting between these. So now we have, these are the new tools that we can use to interconvert between alcohols and carbonyls and go on to do other reactions. So remember that primary alcohols can be reduced to aldehydes, and if you use sodium dichromate, can be oxidized to aldehydes using PCC. Okay, this is going to be our preferred reagent. I know there were some other ones we talked about, but if you want to oxidize a primary alcohol to an aldehyde, this is going to be the one that you can use. Just go ahead and use that one. We can reduce an aldehyde to an alcohol using our soft reducing reagents, lithium aluminum hydride and water. Could also use sodium borohydride and methanol, or water. And for secondary alcohols, we can use the strong oxidizing agent because those will make a ketone, and those cannot be further oxidized to carboxylic acids. And again, we can reduce those with using the lithium aluminum hydride. So these are our new reactions that are going to be useful in synthesis. So for our synthesis problems for the final exam, these are going to be the new reactions that you might see. So in terms of, remember our terminology with oxidation and reduction, we can apply this also to alkenes and alkynes. Remember that adding hydrogen is reduction, right? So when we go from alkynes to alkenes, we're adding hydrogen. We add two hydrogens. Add two hydrogens. Add two hydrogens. And we're going the other way, it's remove two hydrogens. So that's oxidation. Remove two hydrogens. That's oxidation. Okay. And so likewise, we're seeing this with the alcohols as well. Adding hydrogens, reduction. Removing hydrogens, oxidation. And so finally, we kind of can build this mind map. So this part here on the top, this was already familiar, right? We already seen all of this. What's actually new here? What's the new part? The new part is this right here. So all the other part we've already seen before. But we've added this part going between ketones, aldehydes, alcohols. So this is a nice little summary. If you want to put these on your notes, on your personal notes for the final exam, could be useful. And this is a nice little summary. So all these other reactions we've discussed before. These are the new ones, and these are what you might end up using when doing synthesis. Okay. Finally, Grignard is our new reaction for forming more carbon-carbon bonds. Again, all we had before was the use of the alkylnide ions. The alkylnide ions, remember, like these, the alkylnide, and using these in SN2 as a substitution to add more carbon atoms. But now we have the Grignard. So you're going to want to use the Grignard when you're starting with a carbonyl, and you want to end up with an alcohol with extra carbon atoms on it, right? And then you can go and do extra things with the alcohol after. You remember that if you're starting with an ester, you can add two groups by the Grignard reaction. So this is our new way of adding carbon atoms. And so now you got two options for adding carbon atoms instead of just one. Um, so there's lots of, and when you look at this diagram too, going back, you can see there's lots of different possible pathways, right? If I want to go to an alcohol, I could go in lots of different ways. I can go to the alkene and go to the alcohol. I could go through the alkyne, and so forth. There's lots of different pathways. So there's never any one answer. You do want to use the fewest steps if you can, but you can do, for example, a Grignard reaction to add carbon atoms, and then you can oxidize the alcohol to get back to a carbonyl. Okay, so that's a move. That's kind of a new move for us here. If you're starting with a carbonyl and you want a carbonyl with more carbon atoms, the move is do a Grignard. So do the Grignard, and then after that oxidize, and you'll oxidize your alcohol back to the carbonyl. And so that's a new move that you're going to want to keep in mind. You're going to want to be watching those carbon atoms. When you're adding more carbon atoms, you can use the alkyl ion like we used before, but if you're starting with a carbonyl and ending with a carbonyl, your move is going to be a Grignard followed by an oxidation. That's going to be the move you want. And that's going to be it for our lectures this week. Make sure to practice the homework, practice the synthesis reactions with your new reactants. So I did assign some synthesis reactions from this chapter. These are going to use the new reactions that we've learned in this chapter. And yeah, I hope you have a great week, and please let me know if you have any questions. Have a good one.